Welcome back to the Explainer. Okay, let's dive right in and completely decode the metric system. If you've ever found yourself sitting in an exam, staring at a mathematics paper, second-guessing whether you should multiply or divide by 1,000, or honestly getting totally caught in those notorious area and volume traps, you are in the exact right place. Today, we're taking the dimensional journey of metric measures. We're going to break down the core logic so clearly that you will literally never lose marks on unit conversions ever again. And hey, before we get too deep, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Let's get into it. So here is our roadmap for this explainer. First, the language of measurement. Second, mastering linear 1D lengths. Third, weighing mass and capacity. Fourth, the dreaded 2D area trap. And finally, scaling up to 3D volume. Let's start with Section 1, the language of measurement. To kick things off, let's look at why the metric system is actually just a very simple, very ancient language. You see, it might look like a bunch of random letters, but it's a beautifully logical system once you know the vocabulary. These metric prefixes, they aren't just made up, they're actually ancient. Centi comes straight from the Latin word centum, meaning hundredth. So a centimeter is literally 1/100th of a meter. It's built right into the word. Milli comes from the Latin milli, meaning thousandth. And kilo comes from the ancient Greek kelai, meaning thousandth. Once you understand these roots, it's like a cheat code. You immediately know that a millimeter is exactly 1,000th of a meter, and a kilometer is exactly 1,000 meters. The words themselves are literally telling you what the math is. And those ancient prefixes apply universally across our entire measurement toolkit. Notice our 3 base units here. You've got the meter for length, the gram for mass, and the liter for capacity. You just take those root words we just learned, kilo, centi, milli, and stick them right on the front. So a kilogram, that's 1,000 grams. A milliliter, 1,000th of a liter. It's totally plug and play. Once you lock in those 3 prefixes, you've pretty much mastered the entire foundation of the system. Moving right along to Section 2, mastering linear 1D lengths. Let's see this linear measurement in action. Think of this as drawing a single straight line on a piece of paper. Look at how a multi-step conversion works when we really break it down. Let's say we need to convert 2.3 kilometers all the way down to centimeters. We don't just guess, we use stepping stones. Step 1, we change kilometers to our base unit, which is meters. Since kilo means 1,000, we multiply 2.3 by 1,000 to get 2,300 meters. Easy, right? Step 2, we change those meters into centimeters. Because centi means 100th, we know there are 100 centimeters in a meter. So we multiply 2,300 by 100, and boom, we land at 230,000 centimeters. By visually narrating the zeros like this, you can see exactly how 2.3 kilometers transforms through just 2 simple multiplication steps. So the absolutely crucial point here is knowing whether you should multiply or divide. And this is where a lot of students panic. But it's pure logic. If you were going from a larger unit, like kilometers, down to a smaller unit, like meters, you multiply. Why? Because you're going to need a lot more of those smaller units to cover the same distance, right? So 5.8 kilometers times 1,000 equals 5,800 meters. But if you're going from a tiny unit, like millimeters, up to a larger unit, like meters, you do the exact opposite. You divide. 4,700 millimeters divided by 1,000 gives you 4.7 meters. Whether you're multiplying to go down the scale or dividing to go up, this logical rule of zeros works every single time. Honestly, it's foolproof. All right. Section 3, weighing mass and capacity. Let's see how weighing and pouring build upon the exact same logic. You're going to love how beautifully repetitive this is. Let's look at mass first. What if we have 8,300 kilograms and we need to convert that into tons? Well, step 1 is recalling the rule. There are 1,000 kilograms in 1 ton. Since we're moving from a smaller unit, the kilogram, to a massive unit, the ton, we know we need to divide. Step 2, divide 8,300 by 1,000. And step 3 gives us our result, 8.3 tons. It literally doesn't matter if you're weighing a cargo ship or an elephant in tons. The conversion steps remain absolutely identical to how we handled length. Actually, before we jump into capacity, let me just say, if you want to make sure you're nailing these concepts, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve their grades, so join them right now. Okay, back to the math. Capacity follows suit perfectly. 1 liter is exactly 1,000 milliliters. Think about a standard question you might face, adding 0.88 liters to 650 milliliters.
Now, you can't just add those raw numbers together. They speak completely different languages. But because you know 1 liter is 1,000 milliliters, you can easily change 0.88 liters into 880 milliliters just by multiplying by 1,000. Then 880 plus 650 gives you 1,530 milliliters. So the key takeaway here is that mismatched units are easily solved by just shifting that decimal point according to our base rules. Simple, right?
Now here is where it gets spicy. Section 4, the 2D area trap. Pay really close attention to these square conversions because this is exactly where even the top students rushing through their papers lose marks.
I want you to really think about this question. If 1 meter is equal to 100 centimeters, how many square centimeters are in a square meter? Seriously, think about this carefully before we reveal the answer, because your intuition and all that standard 1D linear math we just did might totally trick you here. Most people, when they see this in a test, immediately shout out 100. Let's see if they're right.
The answer is 10,000. No way, right? It's 10,000. Absolutely not 100. If you guessed 100, don't worry. You are definitely not alone. It's the most common trap out there. But let's look at exactly why it's 10,000 so you never make that mistake on an exam again. This brilliantly illustrates the difference. When we talk about area, we are talking about 2 dimensions. Picture a flat square painted on the ground. That square is 1 meter wide and 1 meter long. If we convert those sides to centimeters, the square is 100 centimeters wide and 100 centimeters long. To find the area, what do? We multiply the length by the width. So 100 centimeters times 100 centimeters equals 10,000 square centimeters. Because we are working in 2D, we have to apply the conversion factor twice, 1 for the length, 1 for the width. That's the secret.
Which brings us to Section 5, scaling up to 3D volume. Once you grasp that 2D concept, you basically hold the key to the final boss of metric measures, cubic conversions. So let's test your new logical framework. If jumping from a 1D line to a 2D square meant we had to multiply our conversion factor of 100 by itself, adding 2 zeros, what do you think the 3D plot twist will be for a cube? Take a guess. Yes, it is 1 million. 1 single cubic meter holds a massive 1 million cubic centimeters. It's kind of mind-blowing when you think about it. Let's break down exactly why this number explodes so rapidly.
Look at how this side-by-side comparison exposes the trap. In 1D length, a meter is just a straight line of 100 centimeters. In 2D area, it's a flat square, so it's 100 times 100. But in 3D volume, we have a cube. It is 100 centimeters long, 100 centimeters wide, and 100 centimeters high. 100 times 100 times 100 is 1 million. This side-by-side comparison reveals the ultimate secret to the conversion trap. You must apply the conversion factor for every single dimension you are measuring. 3 dimensions means multiplying it 3 times. It's like a giant mathematical puzzle, and now you have the master key.
Let's apply this to some actual problems you might see. Say you have 2.5 cubic meters. You multiply 2.5 by 1 million to get 250,000 cubic centimeters. Easy. But what if we look at a tiny cubic centimeter? Well, it's 10 millimeters by 10 millimeters by 10 millimeters. That means 1 cubic centimeter is exactly 1,000 cubic millimeters. And if we need to work backwards, say we have 150,000 cubic centimeters, and we want to find out how many cubic meters that is. We just divide by our 3D conversion factor of 1 million. Move that decimal 6 places to the left, and it gives us 0.15 cubic meters. By visualizing the dimensions like this, these seemingly complex volume conversions suddenly become logical and entirely manageable. We've traveled all the way from the ancient Latin roots of a centimeter to the massive million-fold multipliers of 3D volume. So how will you approach your next conversion question? Will you just cross your fingers and rely on rote memorization, hoping you don't mess up the zeros? Or will you use this dimensional journey to logic your way to the exact right answer every single time? Master the dimensions and you will literally never fall into the measurement trap again. Now here is your final reminder. If you want to consistently beat these tricky questions, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Drop a comment below with your target grade for mathematics and the biggest challenge you're currently facing. Like and share this explainer with a study partner who always gets caught out by the 2D area trap. Thanks for learning with us today on The Explainer. You've got this.